Hello everyone, we're the Calculads, and today we'll be talking about approximating areas with Riemann sums. So firstly, we need to know what is a Riemann sum. So it was named after a German mathematician, and they're used to approximate the area under a curve by dividing a complex shape such as this curve right here into smaller geometric shapes, typically rectangles. So looking at the first example, we have the left Riemann sum. So we can look at it as, this question would be asking, approximate the area under the curve with the left Riemann sum using 4 subintervals. So knowing that, we need to know where it starts and where it finishes and divide this area or this length into 4 different units. So in this case, each unit would be 2. And for the first one, we want to see where does the point of the first interval intersect with the curve from the left side. So in this case, it starts at the origin, and if we're looking at it from the left, that would be the first intersection. So you want to go across 2 and go up to, at the second unit, which point on the curve would it intersect with the curve. So in this case, it would be 7. And for the third one, it would be at the very vertex of the curve at 4, 9. And for the last one, it would be at 6, 7. So knowing these points, we want to draw them into rectangles for each subinterval. And in this case, this one would just be a line across because there's no height to it. And for the second one, it's a height of 7 and it goes across 2. And the third one, it's 9 units high and 2 across. So, and then the very last one is a mirror of the subinterval B. So looking at the area, and obviously this is an approximation because looking at here, this area isn't covered, this little triangle up here isn't, and this part's over covered. So looking at the area, we can find, just multiplying length by width, we can find the area of each subinterval, in this case A, B, C, D. And find 0, 14, 18, and 14, adding up to our approximate area of 46. Looking next at the right Riemann sum, the best way to look at this compared to this is that it's just the complete mirroring of it. So looking from the right side, it has 0 height, this one has 7, 9, and 7. And looking at the area, it would be the exact same but just backwards. So looking, 14 would be here, and then 0 would be here. So it's just completely flipped, and our approximate area is the same. Okay, so the third Riemann sum example is called the midpoint. So instead of finding where it intersects from the left to the right, we want to find the width of the subinterval and divide it by 2, and that'll be the midpoint of each subinterval. So in this case, the width is 2, so we want to divide it by 2 and find where it intersects when x is 1. So right here, our line drawing isn't exactly perfect, but if you put it through a graphing calculator, we will know that this intersects at 4, or y equals 4. And for the other one, or for these two in the middle, since the curve is a direct reflection of itself upon the vertex, so we will know that the height is 8.571. And same for the other one, and A and D are mirrors of each other, so finding the area by using length times width, we can find that our approximation of the area would be 50.284. And for the final one, we have the trapezoidal sum. So looking at this, you want to connect the first intersection as 0, 0 in this case to the one from the right where it intersects the line here. And you want to draw it into a triangle between the 2 points. So from here to here, we know that to find the area of a triangle, it's base times height divided by 2. So the base is 2 units, the height is 7. Multiply them, divided by 2, you get 7 for part A. We know that it's a mirroring, so D would be the same as A. And looking here, we need to know from geometry that if we're looking at an irregular shape like this, we can think of it of more simple geometric shapes where from here to here to here, it would be a rectangle and this would be one together. So we can calculate it as 2 units across to 7 here, and that would be this rectangle. And to find the area of the smaller one up here, we would need to use base times height divided by 2. So base times height would equal 4, and then divided by 2 equals 2. So right here we have, for this section here, or subinterval here, B, it'll be equal to 16, same for C, and our approximation comes out to 46. So what we can gain out of this is to know that all of these approximations of areas using like the different Riemann sum formulas, they're all relatively similar, and without using a digitalized calculator, we can find an approximate curve.
Bye-bye.
Bye.